Hello everyone, Dr. Young here, and in this video we're going to talk real quickly about writing half reactions for redox reactions. So once you know you have a redox reaction, once you know in that redox reaction what was oxidized and what's reduced, we can kind of pull that out and write what's called a half reaction for just the oxidation or just the reduction. That's what we're going to talk about in this video. So I've already kind of mentioned, right? Hopefully you've watched the previous ones. Redox reactions, they're all over the place. From rusting to all your metabolism to fire to batteries to just all kinds of things. It's a super important type of reaction. They always involve this transfer of electrons, and you always have an oxidation reaction occur, and you always have a reduction reaction occur. Because remember that oxidations are when you lose an electron, and so that electron has to go somewhere. And a reduction is when you gain an electron, and that electron had to come from somewhere. So usually these occur at the same time, and hence why it's called a redox reaction for short. And we mentioned that you see a change in the oxidation state. Again, for this one, right? Iron was 0 because it's an element. Oxygen 0 because it's an element. Here we have an ionic compound with the iron 3 oxide. So you just say that the oxygen is whatever its ionic charge is, which is -2. And we can deduce that iron must be a +3 charge so that you have a neutral equation, or neutral compound, excuse me. So we have all these oxidation states. And I know that this is a redox reaction because I see that iron goes from 0 to +3 and oxygen goes from 0 to -2 is the idea. Now for the half reactions, right, the idea is we can split this up. Before in a previous video, I was mentioning that this is a schematic for what's called a flow cell battery. And in it, I have 2 species of vanadium on one side and 2 species of vanadium on another side. Now, again, we're not going to get into batteries for a while. We'll talk about cells, electrolytic cells, and galvanic cells later. But batteries are a good example of redox reactions. You're just moving an electron from one place to another, which is just how you generate a direct current, which is how your batteries work. Now, if I take a look at this here, on one side, I have this side right here, right? I have vanadium 4 going to vanadium 5. So I can write, I'll just use this space right here, vanadium +4 going to vanadium +5. And if I take a look at that, right, vanadium went from 4 to 5, that means this was an oxidation. This was an oxidation reaction. If I take a look at this side where I went from vanadium +3 to vanadium +2, that was a reduction, right? Because we went from +3 down to +2. It must have gained an electron. And so what we're going to talk about in this video is how do we write these half reactions. I've kind of got part of it, but the charges don't balance. So we're going to talk about how to write half reactions of just the oxidation or just the reduction. So how do we do this? Always, 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 like in a lot of chemistry, you need to start with a balanced equation here, right? So we need to start with a balanced equation. If I look at this example I had in a previous video, I have N2 plus O2 goes to NO2. It's not balanced right now. My nitrogens are not balanced, so I'll put a 2 in front of the NO2 to match the number of nitrogens. That gives me 4 oxygens on the right, so I need this here, right? So I've got a balanced equation now, so I'll write N2 plus 2O2 goes to 2 NO2. And I'm going to go ahead and I'm going to put in the oxidation states just so that I can tell what's oxidized or reduced for my second step here. So 0, 0, these are always -2. That means the nitrogen must be +4. So step 2 says write just the element that was oxidized from the equation. And if I look at this, right, I can see that my nitrogen was the thing that was oxidized. And if I look at my equation, I can see that the oxygen was reduced, right? It went from 0 to -2. And again, if this doesn't sound familiar, go back and watch the video about how to identify reduction and oxidation reactions in redox reactions. So what I'm going to do is for step 2 here, I am going to just write, right, just the element that was oxidized from the equation, so just the nitrogen. So for my oxidation, all right, oxidation half reaction. And I should mention that sometimes, right, people will write out the whole word half reaction, and sometimes they'll just write the 1/2 like a fraction, like a half reaction. So if either one of those you see, they're the same thing. So what I'm saying, if I'm going to write just a half reaction, I just need to write the species that are being oxidized. So I just need to say that N2 goes to 2 N plus 4s. All right, so I'm going from the N0 to the n plus 4s. And notice that I'm keeping the number of things together, right? So I had an N2 molecule, so I have an N2 molecule. And here I had two N equivalent of kind of ions. I had two N's that were in this covalent compound, but they're both plus 4. So I had two nitrogens that are plus 4 is the idea. Now what we're saying in this next step, in step 3, is that you have to balance the charges by adding electrons to whichever side they are needed. So if I'm going to add electrons here, so I'm going to add electrons, I need this to balance out in terms of charge, right? I need it to balance the charge, right? To balance the charge. So on the left-hand side, I have no charge, I'm neutral. On the right-hand side, I have a plus 4 nitrogen, but actually I have two of them, so I have plus 8, right? So I have a plus 8 on the right, I have 0 on the left, so I'm not balanced. How am I going to get these to be the same? Well, electrons are negative, so it's not like I can add anything to the left. I have to add my electrons onto the right-hand side to get this to balance, because if I add 8 electrons, the idea is that now the left-hand side is overall neutral, and the right-hand side is overall neutral, right? Because I have 4 positives with the nitrogens, and I have 8 negatives with the electrons. So overall, now this is balanced both in terms of number of atoms, 2 nitrogens, and in terms of the overall charge, 0 and 0. So that would be my completed oxidation half reaction. And you'll notice, this should also make sense, right? We said oxidations were when you lose electrons. Here I had nitrogen with its electrons. Here I have nitrogens that have lost electrons, right? See, now these electrons are like off and available to do something like run a battery or go through an electron transport chain if you're in a cell membrane or something like that. Now we're going to look at the reduction, right? So step 4 just says repeat 2 and 3, but for the reduction, so reduction, half reaction. Now it looks like I've got my two O2s that at oxidation state of 0 are going to 4 O minus 2s, right? And I got the 4 O minus 2s because there were 2 for each one of these NO2s, but then there's 2 as a coefficient. So I have 2 NO2s, all of them are minus 2s, so I broke it up. And again, I need to add electrons to get things to balance. On the left-hand side, I have an overall net charge of nothing. It's 0, right? I just have oxygen zeros. On the right-hand side, though, I have negative 8. So how am I going to get that to balance? Again, I'm adding electrons that are negative. So in order to get it to balance out, and it doesn't have to be neutral, it just has to be the same, I'm going to add 8 electrons to the left-hand side. Because if I add 8 negative charges to the left-hand side, now overall it's negative 8. And then on the right-hand side, overall, it's negative 8. So I've balanced the charges. Again, balancing the charges doesn't mean that they're both 0 or they're both plus 2 or they're both minus 2. It can be any of those. It can be any of those. You just need the charges to be balanced. So then my reduction half reaction would be this right here. 8 electrons plus 2 O2s go to 4 oxide ions. That's the balanced reduction reaction. The balanced oxidation half reaction is N2 goes to 2 N plus 4 ions plus and 8 electrons. Those are the balanced half reactions. So let's try that with some new reactions, right? The biggest new thing here is that we're going to add electrons to these to balance charge. That's the new piece. Let's take a look at this example I was talking about before here, right? So I have, let's start with the vanadium 3 to vanadium 2. So if I have vanadium 3 turning into vanadium 2, that's definitely a reduction. I see that my electrons went down. But again, I need to balance the charge. I have 3 positives on the left and 2 positives on the right. How am I going to fix that? I'm just going to add an electron on the left, right? So that overall, this has a net plus 2 charge to balance out that net plus 2 charge, right? And that is going to be the reduction half reaction. If I do the same thing with the other side, vanadium 4 to 5, also I've got a balance in terms of number of vanadiums, 1 and 1, but my charges don't balance. So how am I going to get that to be fixed? Well, if I add an electron to the right-hand side, then I'm going to have a net of plus 4 on the left and a net of plus 4 on the right. So that means this is my oxidation half reaction. So all I had to do here was add those electrons to get the charges to balance, and then I'm set. And you'll notice that once these are balanced, by the way, while I'm still got this up, you'll notice that the oxidation released one electron, and the thing it was paired with picked up an electron. If you go back a minute and you look at that one with the nitrogen and oxygens, one released 8 electrons, and the other one picked up 8 electrons. And that'll be one way you can check your work. So they should be the same. If you have a balanced equation, the number of electrons that one releases or loses should be the same number as the other one gains or receives. So let's just do 2 more here. Write the half reactions for these 2. Again, I'm just going to go ahead and write in my charges, oxidation states here, oxidation number, so I know what's being reduced, what's being oxidized. It looks like for this case, my sodium is being oxidized. So my oxidation half reaction looks like I've got sodium 0 turning into, 2 sodium zeros turning into 2 Na pluses. That's not balanced, so I need to add 2 electrons here, and now both of them have a net 0. If I look at the reduction piece, right, so my reduction half reaction, I see that I have a Cl2, which is a 0. I have a Cl2, which is a 0. It turns into 2 Cl minuses, 2 chlorides. And again, that's not balanced here. I'm neutral on the left, and I have 2 negatives on the right because I have 2 chlorides. So I need 2 electrons on the left-hand side to get that balanced reduction reaction. And again, looks like in the oxidation, you release 2 electrons. In the reduction, you pick up the 2 electrons. These are the same 2 electrons. They're going from one atom to another atom. So you should probably pause, take a crack at this last one with the silver sulfide and the aluminum sulfide and the silver, and then the silver sulfide and the aluminum. Go ahead and pause, see if you can do that one. So if you come back to this, aluminum should be +3, sulfur is -2, silver is 0. This silver is +1, this sulfur is -2, this aluminum is 0. So it looks like the sulfur didn't change. I think we talked about that in the previous video. But what was oxidized, for the oxidation, I'm writing these different ways so you can just see them. Looks like what was oxidized was the silver, right? I had silver 0, 6 of them, turned into 6 silver plus ions. How am I going to get that to balance? Well, I need to add 6 electrons here so that both sides are overall neutral. So I got overall 0, overall 0. If I look at the reduction half reaction, what was happening with that? It looks like I had 2 aluminum +3s turned into 2 aluminum 0s. So I have 3 positives on the left. I have a 0, which is being neutral on the right-hand side. So that must mean that I need, 6 electrons. 6 electrons on the left-hand side to get that to balance out. So now both sides are neutral. So that's how you write these half reactions. Definitely worth practicing so you can see it more, but now you have a video of a few examples of how to approach these. Also notice in this last one here, sulfur didn't change, right? Sulfur was S-2 and it's still S-2. So it doesn't show up in either of the half reactions because it's not involved in the reduction or the oxidation steps or the parts. So you don't have to put it in the half reactions at all. Sulfur is just completely omitted in this one. And you may see examples in the future where you're just going to omit things like a sulfate or oxides or something like that. So don't be worried if you don't have all of the elements showing up in your half reactions that were present in the whole reaction. So study up, good luck, let me know if you have questions.